Hello, today my topic review is about the current Siamese framework for contrastive learning for visual representation. So let's define the let's given the problem definition first. So our goal is to get the augmentation environment representation. So to get this, first we given one image, we sample two different augmentations from the same augmentation family. So we can get XI and XG, two different augmented images. After this, we input this two images into the encoder F. Usually it's ResNet or something else. And after this, we can get the representation. We call it representation HI and HG. After that, we further input those two representation into a projector G, and then we can get the embedding ZI and ZG, like here. And finally, we calculated the loss using ZI and ZG, and we maximize the agreement. In other words, we minimize the distance between ZI and ZG. So this is loss. So how we evaluate whether our model is good or not. So the metrics we're using here is, first we freeze the encoder and using the representation to do classification with a one linear classifier or something like KNN classifier. So recently there are many works in this field based on how to make the mapped representation, we also call it embedding, close with each other. I summarize recent state of art works into 5 categories. And in this presentation, we will not talk about the clustering-based method. So the first is InfoNCE loss, and second is Predictor, and the third one is Decorrelation-based, and finally the KL Divergence-based loss. So first, let's talk about the InfoNCE loss. So the most famous work in this using this loss is a paper called SimSiam. So how to calculate the loss? Given a mid-batch of n samples, we can get 2n embeddings. ZJ, we call it ZI. And first, we calculate the cosine similarity for every positive pairs. And like the softmax cross entropy classification in supervised learning, we calculate the loss like this. And why we using loss? By using this loss, we can maximize the agreement, which means we can maximize the cosine similarity between the positive pairs, and in the same time, we can decrease the similarity for the negative pairs. Here, negative pairs is that the cosine similarity between the remaining other representations besides the positive pairs. And then there are other two works named MoCo version 1 and MoCo version 2. And for this table summary the SimSiam MoCo version 1 and MoCo version 2, what's their difference? So firstly, these three works using InfoNCE losses. And for MoCo version 1, he didn't have a projector. The projector is the G here. So in MoCo version 1, they calculated the InfoNCE loss directly using HI and HJ. And for SimCLR and MoCo version 2, they calculate the InfoNCE loss by using the projector, the embedding ZI and ZJ. So, and the second difference is that SimCLR and MoCo version 2 using more complicated argumentation, and MoCo version 1, the argumentation in MoCo version 1 is very simple. And there are also other difference between MoCo and SimCLR. So in MoCo, there is one encoder, we call it momentum encoder. And this encoder, we didn't update it by gradient. We update it using the moving average of another encoder. So the second branch is Predictor. So two frameworks using Predictor, SimSiam and BYOL. Here we can see the difference between SimCLR and SimSiam. So in SimSiam, they using Predictor, and the loss in SimSiam, they try to maximize the cosine similarity between the positive pairs directly. It's like this. And other things, they need stop gradient in this side. And so BYOL is very similar with SimSiam. The only difference is that in this side, BYOL will not BYOL update this encoder by moving average with its momentum encoder, just like the MoCo version 2. So the third branch, I call it decorrelation. So there are three work using this method, Barlow-Tins, VICReg, W-MSE. So first let's talk about Barlow-Tins. Barlow-Tins directly apply redundancy reduction principle, which is the information theory principle for a pair of identical networks by making cross-correlation matrix C between ZA and ZB into an identity matrix I. So what they want to do, just like this figure. First, they get the embedding ZA and ZB, just like previous work, and then they get the cross-correlation matrix. The loss is try to make the cross-correlation matrix into the identity matrix. So which means they try to decorrelation the dimension, each dimension in the representation. So here, the loss like this. And the next work, VIC regularization. They decompose the contrastive learning problem into three parts: variance, invariance, covariance. So the most important thing is also here, covariance. So this covariance also have the effect of direct decorrelation. And he can also achieve the comparable performance with the Barlow-Tins. And in this paper, they also cite the variance loss is very initial, because without this variance, the model will collapse. And the invariance is maximize the agreement between predictive pairs. And the third method in decorrelation branch is W-MSE. They formulate the problem as follows. So the main goal is that we want to maximize the cosine similarity between ZI and ZG positive pairs, and they constrain this problem within. They want to make sure the covariance matrix ZI and the covariance matrix of ZJ is identity matrix. So they propose a method called whitening. Yeah, this. So the input, after we get the representation V, and we times it with minus it the mean value and times the WV matrix to get the whitening effect. And then we calculate the loss directly using the whitening representation using the MSE loss. So this three methods, the core idea in these three methods is to decorrelation. And finally, there are another branch, KL divergence. So let's talk about the first work, which is DINO. In this paper, they focus on the dimension level information. So for each sample, DINO makes the output distribution of students align with the decentered teacher distribution. Here, they just, so after argumentation, applied argumentation, we get X1 and X2, and we go through the student encoder, which is just like previously a normal encoder, and X2 goes through a teacher encoder, which is definitely a momentum encoder like previous work. And here it's moving average. So it is the momentum encoder. And here, the output of momentum encoder, which is also they call it teacher encoder, will go through some decentering part, which is a normal operation of just minus the mean value of the representation. After this, they put the representation into softmax, and then they get P1 and P2. And finally, they calculated the loss by KL divergence. They want to the distribution of P1 and P2 very similar with each other. And also they put the stop gradient in the teacher side. And similarly, another work, ReSSL, they call it relational self-supervised learning with VICReg notation. So in this work, they focus on the instance level information. And previously, DINO, they focus on dimension level information. So here, what is the instance level information? So in this work, they will they call the two encoder, and momentum encoder. The momentum encoder. They also have the momentum encoder. They call it target encoder. So for each after we get, so we can get the momentum encoder representation. We call it Z1, and the another we call it normal encoder or student encoder. We call it Z2. And for Z1, we will calculate his cross-similarity between the calculate the cross-similarity for A1 with the memory buffer, all the information in memory buffer, and which is definitely here, PI1. And for the student encoder, we do the same things. We get the PI2, which is we can by do this we can get the distribution for the teacher encoder with regard to the memory buffer and student encoder with regard to memory buffer. After this, they try to make the distribution between these two encoders same with each other by maximize the KL divergence here. So KL divergence, since this HP1 has no impact, so they just remove it, so we get the friendly loss, which is minus P2 log P1. So the key point in this work is make the similarity distribution and memory buffer of student encoder same with target. So this work and DINO is not very similar with each other, but they both try to using the KL divergence to calculate the loss. And they both of them have the stop gradient and the momentum encoder. Here, momentum encoder, and both of them using softmax. Oh, okay, thank you for your listening.